So welcome everyone to the session of Introduction to Deep Learning. Like I told you, I'm going to first go to some theoretical concepts, the idea behind, the inspiration behind deep learning, and what is actually driving the whole deep learning initiative, and some of the core concepts, the core construct of deep learning, some of the fundamental components, and how the whole process of learning happens in the deep learning. Right? I'll give you some of the mathematical intuition also. We'll go through that. And then later we will go through the hands-on exercise, right? So I have shared the link on the chat window to the GitHub location. And we'll go through in the next half of the session today. Okay. So of course, I want to start with this particular slide. You might have already seen. And so if you look at artificial intelligence, right? So any mechanism that you can actually build in for a machine to take decisions like humans, right, can be actually fall under artificial intelligence. For example, there are two kind of systems. One we call it at a high level. One we call it an explicitly programmed systems. Right, explicitly programmed systems and not explicitly programmed systems. By the way, I just want to confirm if you are able to see also what I'm writing on the screen.
Yes. Yes, Professor.
So explicitly programmed systems are traditional systems which are called expert systems or rule-based systems. Right. So rule-based systems are also kind of AI systems because we kind of, explicitly programmed like a software, right? If-else statements to take certain decisions given certain conditions on our behalf, right? So you can automatically take decisions. If you look at some of the traditional fraud detection systems, also primarily based on rule-based systems. But those systems are extremely complex to manage and very slow to adapt to the changes in the real world. Because today, if you look at the business world or any, right, the world changes very fast. And you observe that, understand that, and then program that into a system takes a long time. So adoption to the changes very, very slow. So people started falling into something called not explicitly programmed systems, which are primarily automatically learning from the data. What is data, by the way? Data is nothing but your past experiences, right? Your past experiences, which are nothing but your samples. So if I take an example of fraud detection system, right? In the past, you already have experience on frauds and non-frauds, right? But why they are frauds and why they are not frauds, we are not getting into that. We're simply taking those samples and asking an algorithm to learn from it. So that's where machine learning systems came out brilliantly, right? So we have a statistical learning and a machine learning. Both kind of systems are there. So these systems typically learn from data. They are not explicitly programmed. They learn from data. And what they learn a function. Primarily, they learn a function, right? So you can say if y is a FFF, x1, x2, x3, and xn, and so on and so forth. And these are the factors or features influencing the outcome. And this is the outcome. And those experiences in terms of samples we have collected. Now, if we give that to the machine, it automatically understands or learn this function. So learning this function is the most important part, okay, in machine learning. So machine learning is kind of a subset of artificial intelligence, right? Not explicitly programmed systems. But one of the key limitations of machine learning systems are that primarily, if you look at all our traditional machine learning systems, they talk about your typical linear regression, logistic regression, decision tree, random forest, boosting on all the systems, they were primarily designed to kind of work on a structured data. And that was fine because if you look at 10 and 15 years back, mostly people were working on the business data, right? Organizational data coming out of their systems, like a traditional, OLTP systems and all that, where they capture the system of records. But what happened is in the last 10 to 15 years, there has been a lot of interest, a lot of use cases that has emerged out of what? Unstructured data, especially three kinds of data. One is natural language, NLP. One is computer vision, your images and audio. Okay. Though, of course, there are some applications of machine learning in those areas, but those models were not very accurate. Okay. Because in typically unstructured data, the patterns are so complex and the dimensions are so high that machine learnings typically do not perform well. And machine learning and then there was actually a benchmark, which is of course one of the finest empirical evidence. They found that if you look at the amount of data that you actually use to learn a system, a function, right? And if you look at the performance on the y-axis, this is x and this is y-axis, as you increase the amount of data, right? Typical traditional systems, initially they perform better as you increase the amount of data. But after a certain time, they actually tend to saturate. Okay. That is primarily for two reasons. One is in the structured data, especially, there aren't as complex relationship or function like in unstructured data. And second one is also the models typically are simpler models. So they don't have something called universal approximation function. We'll come to that. And then they typically tend to saturate. And then they found that your typical neural network models, which are primarily renamed as deep learning, they tend to learn better as the data increases. Okay. So there is a nice concept called unreasonable, right, effectiveness of data. Okay. Unreasonable effectiveness of data. It's a nice paper there. Actually, if you want to read, you can read that. I think it's by Google. So without changing the model, I mean, if you just increase the data, that typically the models tend to perform better. And that even better, especially when you're using deep learning models. And deep learning models can also be categorized into three different buckets. One is small neural networks, basically small in terms of number of parameters that you're going to estimate. We'll look at what are those parameters today. These are medium-sized parameters and a large number of parameters. So your large language models typically fall onto this particular category, where you're talking about 100 billion parameters, right? Billions of parameters. They even tend to work much better, right? That's why the deep learnings have actually a lot of interest actually generated in the deep learning. One of the important case study that you should all be aware of is called ImageNet case study. In fact, this was, I think, about 2011-12 times, where Stanford actually collected data, image data, about, I think, about 1.4 million images and about 1,000 categories. So these images were like, this image is a person, this image is an animal, this image is this particular plant, right? And all that across 1,000 categories. And they launched a competition and basically asked people to kind of build a model that can automatically learn, like object identification. Given an image, it can automatically predict or understand what the image, detect what the image is about, what entity it is. And before that, we never had so much of samples data. Okay, this is for the first time. We had actually so much of sample data collected and given as a training samples. And in that competition, what happened is, for the first time, somebody built a deep learning model, those times called artificial neural networks. and it came out as a top contender. So it gives actually accuracy probably more than 90%. And the second best is a traditional ML model, so almost 8 to 9% lesser than that. Okay, so all of a sudden, people realize the importance of an artificial neural network, especially when the sample size is extremely large. Okay, and since then, of course, deep learning model has been learned. I mean, the same ImageNet competition is run every year, and year by year, of course, every time the deep learning models are winning the competition. And what happened is by 2015, the models have performed a better than human level performance index. What does that mean? How can we be better than human levels? You're asking a human to kind of look at the image and ask what object it is, and you're asking an algorithm, and the algorithm is doing it better than humans. So what they did is also, of course, some of the images, they actually added a lot of noise, like a blur. And humans could not detect the image, whereas the deep learning models are able to identify those images. So that's where, of course, a lot of interest got generated, saying that, okay, deep learning models are actually able to understand very, very complex patterns in the data. And it's, of course, can perform really well, and especially in the domain of unstructured data. Of course, the initial research and all the advancements have happened, especially in the computer vision domain, CV. But later, we caught up with the natural language. And today, probably natural language is the most important use case, especially as far as deep learning is concerned. So there are two factors that are driving this whole innovation, right, and adoption of deep learning. One is the availability of large data sets. And today, if you look at the same ImageNet, they've increased the data set to almost 1.4 million, 14 million images, and across 20,000 categories. And the second one is the rise of GPUs. So as the number of parameters increased, people started building larger and larger neural networks, and more data was available. There was also a need for, high computational resources, very large computational resources, which can actually do this computations, especially matrix multiplications, all that faster. So people already saw that GPUs, which are primarily designed in the earlier days, primarily for gaming, they were actually best suited for this, right? And they can do computations much faster. So your availability of data, large amount of data, and availability of better computation in terms of GPU, this basically drove the whole, advancement in the deep learning in the later years. So now this is, of course, a basic context to that, but then we have to go back and understand what exactly is deep learning, right? What are the basic construct or basic elements of the deep learning and how they actually work? So what I'll do is I'll go and start with that now. So the whole deep learning is actually inspired by the structures of the brain, right? The structures of the brain. So if you look at, there is actually a model built by probably neuroscientists saying that this is how the brain functions. So they told, okay, the brain actually contains billions of neurons. Okay. And these neurons, which has a nucleus, okay, receives signals from something called axons from other neurons, right? And then it sends signals to the other neurons. So all these neurons are interconnected, and they send signals from one neurons to the other neurons to the axons. And these neurons actually have a function. It receives the signals from the other neurons and then transforms the signal and sends to the next level of neurons, right? So when they collectively work, right? So whatever the input signal is there, maybe the signal is from the retina looking at an image, or let's say eardrums listening to a particular voice or audio, okay, and then they convert these signals through these neurons, billions and millions of neurons, and later, and these signals convert into certain kind of actions or reactions that we have, all right? So same thing can be applied, okay, can be to solve our typical problems. So what actually the deep learning, when they actually design, the most fundamental component is called actually a neuron, or also called a perceptron, right? And it's this, the perceptron is also designed like a, inspired by the structure of the brain's neuron. So the perceptron is nothing but a component, right, which actually receives signals from the other neurons or input signal. Like let's say it receives signal, let's say x1, x2, and x3. And all these perceptrons, a single neuron typically does two-stage function, right? Two-stage processing. Right. So what is the two-stage processing? First, it accumulates all that information. Okay, you can write like a summation function. It accumulates all the information that is coming from the other neurons. Then it does something called a transformation function. It transforms that particular, the total signal that is accumulated here, and transforms it in a way that is required to the next level of neuron. This is, of course, based on a particular objective that we want to solve a particular problem. There are many different transformation functions are there. We'll come to that. And these transformation functions are typically called activation functions. And what it does is, all these signals that's coming from the other neurons, they don't come as it is in its original form or original strength. That actually gets moderated. Moderated by what? Moderated by something called weights. So you can say the x1 signal is moderated by W1 weight, x2 is moderated by W2 weight, and x3 is moderated by the W3 weight. And then this particular summation function, for example, you can think like the output of this particular neuron based on this three particular input would be, right? The output of this particular neuron would be nothing but W1 x1 plus W2 x2 plus W3 x3, right? And of course, we have to add some kind of bias term, okay, to basically kind of say if the input signal is more than a particular level of threshold value, then only the output gets triggered, right? So basically you can add a particular bias term to this. And then you can think like there is a transformation function, let's say G, okay? So the G function will transform this, and that will be the output of this particular neuron, right? And this can be, of course, written in a very generic form. For example, if you have a n number of inputs, right? N number of inputs, you can write in a very generic form, like a G of function, summation of xi, wi, right? Where I equal to 1 to n plus b, right? It's going to be like this. This is the output of the. So this is a basic construct. Of course, what we can do with this, that's most important thing is what exactly we can do with this. Now let's take a very simple example. Let's say we have a one single sample. I'm just starting with the one single sample. Now, if we know the some information about a particular house, right? For example, what the square feet of the house and how many bedrooms that particular house has, can we predict what price the house can be sold? Okay, so you can think like there are two inputs, x1 and x2, and this is basically your y value. Now, this perceptron can actually act like a function, which can transform these two values into the price, right? So if you can know these inputs, you can convert this particular outcome. This looks like a very simple regression model, right? So what you can do is you can get these two signals here. One is your square feet, and then number of bedrooms. And then your output is nothing but your price. So here what we'll do is we'll actually have a summation function and G function. And these two values will be moderated, W1, W2, and there'll be a bias term, threshold value. Right? So here, what you can write the price, okay, will be nothing but your G of W1 multiplied by your square feet plus W2 multiplied by the bedrooms plus some bias value B. Right? And then if you see in this particular perceptron, we have the information about the square feet. We have the information about what? The bedroom. All that you have to learn is what? How much the W1 should be, and how much the W2 should be, and how much the B should be, and what this particular function should be, so that I will approximate these two values now to the price. Approximate with some amount of error. So now that's why these are basically estimated now. So these are your W1, W2, and B are nothing but your parameters. Of course, this looks very, very similar to your regression model, isn't it? This looks like very, very similar to regression model. Now, in this case, what I can do is to kind of simulate the typical linear model. This transformation function G can also be a simple pass-through function, right? Not necessarily it has to, transform. It'll basically say whatever the summation values, I will just pass through it. It will not transform it. So it either can transform or it can also do a pass-through function. For example, let's say there is another example. Let's say I want to find out, given the two health parameters we have, like a blood pressure and a sugar level, right, of a person. Now, can I predict what is the probability the person might be having a coronary heart disease? Now, let's say the blood pressure is, let's say, 150 and sugar level is 200 and the probability is high. I'm just giving an example, all right? So now if you remember the probability values, right, the likelihood of somebody having a disease, the probability value will typically remain between 0 and 1, right? So now in this case, what happens is when you do a summation function with the W1 and W2, so we'll say, okay, 150 multiplied by W1 plus 200 multiplied by W2 with some amount of bias. Now this value has to be transformed in such a way that the output will always remain between 0 to 1, right? So in that case, I have to actually moderate the output through a activation function. And we know there's a function called sigmoid function, right? If you know sigmoid function, whatever the input that you give, it will always moderate that signal into between 0 and 1. So I can actually use a sigmoid function here, right? Which will, predict between the value 0 to 1. So I take all my inputs, I moderate them through the weights, add a particular bias term, threshold value, then I choose an appropriate transformation function, and I approximate to the outcome that is expected, okay? So that is basically the function of a single neuron or a perceptron. But if you look at both these examples that I given, whether estimating the price from the square feet and the bedroom, or estimating CSD from the blood pressure or sugar level, this almost mimics like a linear regression or a logistic regression. Okay, nothing more than that. So a simple function of a one particular perceptron is very similar to a simple linear regression or logistic regression. But of course, in the real world, we don't have something like this, right? We have a much more complex patterns. So we have probably variables which are hundreds of variables and thousands of or tens of thousands of samples. And the relationship between the input output is typically not a very linear. It will be very complex and non-linear, right? So there is a theorem called universal approximation theorem, which says that if this is the x and this is the y value, right? And the function, let's say, looks very complex like this, extremely non-linear, right? And very complex. We can't even capture through this any particular simple function. So the universal approximation theorem says that the neural networks, right? So here I'm not talking about one single perceptron. Neural networks is nothing but a collection of perceptrons, right? Neural networks can approximate any function. It does not matter how complex that function is. If you take not one, but many perceptrons and connect them together and probably arrange them in layers, then they can take any signal, input signal, and transform that to a particular outcome, okay, which might follow any complex function, right? So that's basically the beauty of neural networks. So now we come to the concept of neural. Then what is a neural network? A neural network is nothing but a multi-layer perceptron, right? So here we don't have one single perceptron, but many perceptrons. But unlike brain, where there is no structure, or probably there is a structure we don't know, everything is connected with everything. We cannot have that kind of structure. Then we cannot really mathematically solve it, right? So there has to be some kind of structure how these perceptrons are connected with each other. So they came with this idea, something called layers. So let's build the layers and let's these neurons are arranged in layers. For example, every neural network or multi-layer perceptron will contain three things. One is called your input layer, and one is called your output layer. So the number of neurons that you see are the inputs, and the input layer typically would be determined by the number of inputs we have, right? For example, in our case of predicting the price of a house, probably two neurons, right? One is square feet or bedroom, or probably if you take more number of features of the house, that means number of inputs. Output layer will contain number of neurons based on the problem that we are solving, right? For example, in case of a regression, okay, you must be knowing regression, you're basically predicting one variable, continuous variable or a numerical variable, like predicting the price of a house, predicting the sales volume, predicting the price of a stock, or predicting the rainfall, right? So regression problems, if you are solving, then typically output layer will contain one single neuron, because that neuron's value will be taken as the Y value. But let's say you're solving a problem of classification, right? Like, for example, if you're solving a problem of the sentence is a positive or negative, right? So this is basically a binomial classification, isn't it? Binary classification. So here also we could probably need just one neuron, output layer. If it says the probability is 0, right? Probably is a negative sentiment. It's probably 1.0 or higher probability than positive sentiment. But if you're solving a multi-class problem, where you're basically classifying into multiple different categories, I mean, just to extend this example itself, we'll say the sentence is positive, negative, or let's say neutral. So that would be a multi-class problem. Then we need more neurons. So probably we need 3 neurons. So these neurons probability will specify it's a positive or negative, it's a negative or neutral, right? And the summation of all these probabilities would be equal to 1. Okay, we'll understand that later. We will use a function. So in a multi-layer perceptron or a neural network, artificial neural network, the number of neurons in the input layer and the number of neurons in the output layer is typically determined by the data we have and the problem that we are solving. But what we can actually configure and experiment with is the hidden layers. So this actually adds complexity and can actually help you to build a very complex function like a universal approximation function. So you can actually have something called hidden layers in between, right? You can have 1 or more hidden layers. And each hidden layer, you can have multiple number of neurons. And totally, we can actually call this a artificial neural network. And in this, each hidden layer, the neurons are connected with all the neurons in the previous layer. For example, this particular neuron gets signal from all these neurons in the previous layer, right? But of course, all these signals are moderated through some kind of weights. And each hidden layer, the neurons in each hidden layer will also send signal to all the neurons in the next layer. Okay, so that's how it is actually interconnected in the neural network. Okay, so what I'll do is I'll explain through this simple example now, little more complex example. Then how basically this model learns. Now take a example of, let's say I have two inputs here. X1 and X2. So X1 is basically your square feet and X2 is your bedrooms. Let's say 2 neurons are there. And then I'll build another hidden layer with the 2 neurons. And then there is a layer called output layer, right? So this is basically your square feet. This is basically your bedrooms. And this is basically your output layer. This is basically your price. And now, of course, these are the hidden layer 1, okay, with 2 neurons. This is your input layer. This is your output layer, right? And this is a neuron, let's say N1 and N2 in the hidden layer. So this signal is, of course, connected to this and this. And this is connected with this and this, right? Similarly. So now let's call this weight W11, W12, and this is W21 and W22, right? And let's call this W31 and 32, just for basic understanding. We'll do that. And this will be your B1, this will be B2, and this will be B3, right? Now, if you say, now how do this is my Y value. Now, how this Y is actually estimated from the X1, X2, this is very simple. So what is the output of the neuron 1 would be? The output of the neuron 1 would be equal to, for the timing, assume that it does 2 functions, right? Summation and the transformation function. For the timing, we will actually assume the transformation function to be a simple pass-through function. Okay, it will not transform anything, just accumulates and sends to the next level. So your output of the first neuron would be your W11X1 plus W12X2 plus B1. Okay. And output of the next neuron, ON2, would be W1 to X1. So W1 to X1 plus W2 to X2 plus B2. Right. So first it transforms to some intermediate outputs O1 and ON2. And now my Y function here would be nothing but my ON1, the output, multiplied by W31 plus ON2 multiplied by W32 plus B3, okay, will be my Y value. Okay, you see, it's a little more complex than the simple linear regression, right? So you're actually transforming the function to some intermediate outcome, which might probably, represent some inherent information in the house, which now gets transformed into the price itself. Okay. Of course, this is between only one single hidden layer with only 2 neurons. Now you can imagine when you take, hundreds of neurons or multiple layers of network, it becomes extremely complex now. All right. Very hard to understand. But in this whole thing, if you see in the network, what is known, what we know is only what? Only X1, X2, and the Y. We don't know anything else. Everything else is what? Unknown. They are parameters, right? So in this case, if you see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 parameters are there, right? There are 9 parameters are there. Now the question is, how do we estimate this parameter so that whatever input that you're going to give here, right, how can it actually approximate to the Y value? Okay. I think somebody had a question, so I will just wait here. Please go ahead and ask the question.
Hi, Manoranjan. Thank you for the session. Himanshu here. Just one thing. I mean, for the last, when you are estimating Y, so you don't need a tuition function there in the last, for the last neuron?
No, not necessarily. In this case, at least in regression, you don't need activation function because this is continuous value only.
All right.
Yeah. If it's something like probability value, typically you would need a activation function.
So, okay, so while, okay, just before that Y, when just before last neuron, you don't need that, but before that you need, right? Here.
Here, huh?
In middle layers.
Yeah. You can have it, and no need to also have it.
All
It
right.
all depends on, right? It can be a simple pass-through function, or it can be also a transformation function. Okay. Here you can have it. Absolutely, you can have it, right? But here, of course, you typically don't use it. But for in this particular example, to explain it a little better, I'm not using it, but of course, you can have it. You can have some transformation function.
All right.
Okay. Yeah.
Thanks.
Now, the question is, how do you even estimate these parameters? So let me quickly show that. That's the most important part. Is, let's say I have a signal X1 and X2. And then I have a neurons, hidden layers. Right? And then, so this is W11, W12, W22, sorry, W21, and W22. That's called B1, B2, W31, W32, and B3, right? So the way these networks learn these parameters, you can think like in iterations, okay? So let's say in the first iteration, iteration 1, okay, what I'll do is, I will randomly initialize these weights. So when you don't know anything, the best thing is what? Randomly initialize. Okay. Of course, you can follow certain patterns. For example, you can sample it from a distribution, like a standard normal distribution. But anyway, you can simply randomly initialize these values. Okay. And then what you do is you give this samples here. So you give the square feet 502 and see with all these random values of W1, W2, B1, B2, B3, what is that price that you are getting? Okay. Let's call that yi hat. Okay. Your price is nothing but the actual y. This is the y value. Let's call that yi hat. Okay. So this is the first sample, second sample, and third sample. So typically we write hat as the estimated value of the y, the predicted value of the y. Right? So let's say we get a value of 5 here. And we get a value of, let's say, 12 here. And get a value of 21 here. Right? So whatever the initial values of w are there, we get something like 5, 12, 21. So these are predicted values of the model. And this is the actual value. So then we know that some difference is there. Okay. The whole idea is to what? Minimize this distance. Right? So to do that, what we have to do is, like any machine learning model, we need to define something called an error function. Right? Or we also call it a loss function. See, in machine learning, deep learning, we can always learn a function, but it will always approximate with some amount of error. Right? So as long as this particular error is minimized, okay, through some mechanism, then we know that we got the optimal function, which can approximate to the y value, and that we can leverage to predict in future. That's our model. Typically, models will never exact to y, will always approximate to y with some amount of error. But as long as this error is minimum acceptable, then we can take this model as the most optimal model. Right? So that's why we need to define what is this error here is. Right? So here in this case, because we are kind of solving a regression problem, our error function is what? Typically, we use something called MSE, or mean squared error. Okay, it's called mean squared error. What is mean squared error? I think most of you will be familiar with this. So we look at what is the actual value of y minus the predicted value of y. Okay, we take an average of it and then square it. Especially we square it because either you can do an absolute value or squared value, because sometimes we predict lower and sometimes predict higher. So the error will be positive and negative. They might cancel each other, or take a square value of it. Especially we take square value because it might be a parabola function, but this is how it is, mean squared error. So what we do is, in the iteration 1, after we initialize these values randomly, we input our samples like 502, then 1003 and 703, and basically calculate all those values and then calculate the MSE. What is the loss we are making? We calculate the loss we are making in the first iteration. Okay, so this process is called feed forward. This process is called what? Feed forward. Okay, in the first iteration, we're feeding the data and do all forward computations. Okay, we take the signal, multiply with this, add to bias, transform it, again, multiply by this, summation, and then get feed forward process. Now, once we calculate, then we do a loss calculation. That's a whole step from giving an input to calculating the loss function is basically called one feed forward. Then what you do is, now the objective is to what? If the loss is very high, how do I bring down this loss? All right. The only way you can do is by adjusting these weights, because that's the only thing that we have in our control, the parameters, right? So we use a technique called back propagation now. The error is back propagated. Right? The back propagation. The back propagation process, what we do is, we estimate how much of these weights has to be adjusted. For example, the W11, how much it should be adjusted, the delta value of W11 was basically estimated. Okay. Of course, this estimation is complex. I'll come to one technique, how it's done. So we estimate the delta value for every parameter, right? We estimate the delta value for every parameter. Okay. So this process is called what? Back propagation. So once you calculate the loss function, you adjust all the weights, right? So that these new weights will be estimated now. So W11, let's say dash. This is the new weights after the adjustment happens. Now we repeat the second iteration. Now with the new weights, we again give these inputs to the network and recalculate the Y value. And again, we calculate the loss function, right? So what it is in iteration 1, right? We do a feed forward. Then we do a loss calculation. Then we do a back propagation, right? And then we adjust those weights, right? So in let's say in iteration 1, we get a loss of 1. And then once we adjust the weight in iteration 2, we again do a feed forward and calculate the loss value, loss 2, right? Again, we adjust the weights. So we keep on doing in multiple iterations until this loss that we see is not getting any lesser. It's not getting any lesser. Okay, as simple as this. That means we assume that it probably would have reached the minimum point. Okay, it's of course a little more complex than that, but basically conceptually this is. And then whatever that weights at that point estimated becomes the final estimation of those parameters. Right? And then we take that model for deployment. So in the multi-layer perceptron, in the feed forward back propagation, yeah, go ahead. Somebody asking a question.
Yeah. Hi, Manoranjan. Thanks for this session. One quick thing for the delta weight, even those are random values. Like, how do you know what is the difference to put to improve the value?
Yeah, that I'm coming to that. So that's where actually we do something called, we use something called optimizer. Okay, something called optimizer. Let me take. Okay, so that's whole process basically called an optimizer. Okay, so optimizers basically estimate this value of the delta. Okay, so one of the optimizers is called gradient descent. Okay, so let me explain that little clearly here. That's an important concept to know how much delta has to be estimated. Now, let's take your MSE function. Now your MSE function, okay, this was simple example explaining that. MSE function, if you look at, I'll take one example of a one single weight only, W11, okay? Now it can be expanded to other weights. So as we change the W11 value, okay, your typical MSE function that you see might look like a parabola function, okay? Okay, but this may, of course, look like a much more complex function, but easier to explain, so I'm basically explaining through this. Now, if you know, these are possible, this x-axis basically represents the possible values for W11. And for every value of W11, there is a value of MSE that we have. But the most optimal value is what? In this case, this is the most optimal value, right? Because that is the value where the MSE is what? Minimum. So if you can estimate this W11 to be this particular value here, then I think we have reached the minimum point, and that W11 is basically the most optimal value estimation. But of course, when you randomly initialize the W11 initially, it can fall anywhere on this axis. Yes or no? So let's say assume that when I randomly initialize the value of W11, okay, the value is here. Okay. And when the first iteration I did all this feed forward and calculate my MSE, this was my MSE. Okay. That's the first iteration, iteration 1. I randomly initialize this value W11 dash, let's say, W11 dash, and I calculate the MSE function, and that was MSE 1. And then I know that my optimal value, okay, typically is to the right of this, right? And what we can do is, at this particular error function, we can calculate the slope of the function, right? And the slope of the function is nothing but your DMSE by DW11. And the DMSE by DW1 will have a sign, isn't it? It will be positive or negative sign, depends on, right? The slope is going downwards or upwards, right? So in this case, at this point, the slope is downwards, right? So this value will be always negative here this side. Then what I can do is, my delta would be, in this case, the new value of W11 dash dash, the next value would be W11 dash, right? I can say minus of it, the DMSE by DW1. That means whatever values that you randomly initialize, at that point you calculate the slope of the function and then simply subtract from it. Now, how it's going to help? Because this value is going to be negative. So negative and negative becomes what? Positive. So the next value of W11, okay, will always be larger than what? This particular value of this. That means now what will happen is the next value will be this side. So this will be W11 dash dash. Right? Again, what you do is you take that, again slope, and subtract from it. The next value will be here. You can see that you're slowly moving towards the optimal point now. So after many iterations, there's a possibility that we'll come to this particular point here, where automatically this value becomes 0, because this the slope value is 0. Right? Now, imagine when you randomly initialize the value of W11, it was actually on this side, not on this side, it's on this side. Let's say this value was randomly initialized. All right. So in this case, the slope is positive now. That means when you subtract it, the next value of W1 will be lesser than the initial value of the what's initializing. So it'll be on this side now. Right? So if you see, through this technique of gradient descent, this is called a gradient descent, right? Whatever values that you initially initialize, randomly take, you subtract the value of the slope from it, and you keep doing that, so automatically it will slowly come to the optimal value of it. Okay. So what we do is the delta value that we calculate, right, to adjust, right, this particular weights are not randomly taken, but actually estimated through this particular technique called gradient descent technique. Does that answer your question?
Yes, but
Okay.
there is still one doubt over here.
Mhm.
Over here, we have taken the error to like be represented like a parabola. But what if some parameters they don't? I mean, it appears more like there is a linear relationship between the parameter. That is like as your error increases, that means you are going a little away from the point. But there might be some parameters that are dependent on other parameters, and accordingly, like this thing may not really be a parabola. In such a
Yeah.
case, how would the slope thing work?
Yeah. So there are two things. One is See, one is that your error function, right? The two possibilities are there. Your error function is a convex function or not a pure convex function. That means it has a global minima, right? There's a global minima point, or the function might look something like this, right? Some random function like this, isn't it? Okay. So
Yeah, got it. Now I think so. I get the concept now. Yeah.
they could be local minima or global minima. So there are actually advanced version of this optimizers are there. Okay, like a gradient descent, there are advanced versions of this are there. For example, momentum, Adam optimizer, RMS prop. So that's basically, it's more about using the right optimizer to actually arrive at the minima point. Okay. But of
Yeah,
course,
thank you very much.
yeah. What I explained is from a simplistic perspective, it's a possibility, but actually it can be made complex and you can use advanced optimizers to reach that particular point. Okay. So now if you go back and look at the perceptron a little bit, so there are certain terms that you should be very aware of it. One is so one is you have input layer, one is you have output layer. The number of neurons in the input layer are typically determined by the number of inputs you have. Number of neurons in the output layer is determined by the problem that you're solving, regression, classification, multi-class, and all that. And then you have a multiple hidden layers in between, right? With the number of neurons. And then all the neurons are connected to the other neurons in the previous layer and to the next layer, right? And these connections are moderated through something called weights, right? W. Now, given you have a sample set, right? You have a data where you know the inputs and outputs like supervised learning, right? What you can do is you can estimate these weights that are the connections represent through a process of feed forward and back propagation. So you give the inputs, we estimate the output, right? So you give all the samples in the step one, right? You feed all the samples, you randomly initialize these weights, then feed forward and calculate the loss, how much loss you're making, right? That's basically your feed forward process. And then you do back propagation. In the back propagation process, right, what you do is you look at how much loss it is, and then you calculate the adjustments that you want to do, the delta ones, right, through optimizers, like a gradient descent or Adam or whatever. So whole objective is to what? How to actually bring this loss, okay, or reduce the loss in every iteration, right? In every iteration, we'll actually look at an example when you run the code, right? Every iteration, you bring that to lesser and lesser level until you reach a point where you see that no more adjustments can be done because it already reached a minimum point. Okay. Then you take these weights as basically your final estimation of the parameters, and then that becomes your model, right? Then you give the new input, and whatever weights are estimated, based on that, you make a prediction, right? So that becomes the final prediction of the models. Yeah, please go ahead. I think Himanshu, go ahead.
Yeah, Rajan. So just to summarize, I mean, feed forward and back propagation. So every time we have weight and that neurons, perceptrons, we are calculating that what is the loss value, right?
Correct.
And in back propagation, we are adjusting the weight,
Correct.
right? And every time weight is adjusted, it again goes to the forward propagation, the feed
Correct.
forward.
Correct.
That okay.
That goes on continuously.
Continuously.
When it comes to a point when we cannot minimize the loss anymore, that we assume that, okay, probably these are the best weights estimation that we can have, optimal weights.
Right. Thanks.
Yeah. Yeah, Almavis?
No, that's it. I mean, I don't know how to remove my hands up. Okay, so
Okay. That's fine. That's fine. One more. Abin? Abin, go ahead. We can't hear you.
Yes, sorry. Can you hear me now?
Yeah.
Yeah. So basically, the question that Almanes asked, like the optimization that we are choosing it may be parabola, it may be a linear function. So do we use only one, or we use almost all the optimization that are available, or is the data always same? Like, because every neuron, it may have a different kind of a, like it may be parabola, and the second thing, it may be different. Is there a case like that?
No. We don't calculate the loss at every neuron. We calculate the error at the loss at the final neuron. Because
Okay.
ultimately we can calculate the loss at the Y value because we don't know the intermediate values, right? But this is only we have the actual value in the sample and what is the final predicted value and then minus that predicted value and calculate. So loss function is calculated. Loss is calculated only at the final neuron.
Oh, okay. Got you. Thank you.
Okay, there's one more concept I will explain that is before we get into hands-on, there are two more concepts. One is called learning rate. For example, if you see this is the gradient descent technique, right? That we explained now. So you can think like this is your weights or beta parameter or W parameter. And this is your MSE. And this is your function, okay, convex function. If you use a simple linear regression, right? Simple linear regression. So the error function will look, of course, look like this. Right? For neural network, of course, it won't be look like this. Is all a little more complex than that. And this is the minimum error. So that's the optimal value of the beta value. Okay. But if you look at some error function, even when it's a convex function, right? Some error function will look like very steep. It all depends on the values, right? And some might look like a little shallow, like a valley. Okay. They'll be convex, but it'll look like this. What might happen is if you look at the W and MSE value, let's say it's very steep, like this. The slope value is very large. So when you take a derivative or a slope and say W minus D MSE by DW, this value will be very large. So it'll sharply descend because the value is very high, the subtraction will be very large, sharply descend, right? Then again sharply descend. And it might so happen that because the descent is very high, it might actually overshoot the minimum point. Okay, it might overshoot because you make an adjustment here, directly goes from there. And if it overshoots, it might so happen that it might start, but then again come back, go back, right? It might fluctuate or oscillate around the minimum point, not reach the minimum point. Okay, this is one of the problems that we can actually observe that. Then what we do is we moderate this step size, that adjustment that we do. So rather than subtracting the complete slope, we multiply with a alpha parameter. We're saying that whatever that slope value is, we only take a fraction of it. Okay. So this alpha is called a learning rate. This is called what? Learning rate. So we multiply this rate, how much we do it. Normally we use a value of 0.01 or 0.001 and all that. Because if you take a smaller steps, right, it might take a longer, more number of iterations, but it will probably guarantee you that it will reach a minimum point. Right? So the ultimate function will typically, the optimizer function will look like this: W minus alpha D MSE by DW. Okay. So this is your learning rate, which is also a hyperparameter, by the way. This can be adjusted. Okay. We'll do that in hands-on. We'll adjust this and basically look at how it actually does it. So I think I have a diagram also. Let me see. Yeah. So this is a learning rate. So if you take a very small learning rate, it'll go very slow. Right. And if you take little lesser, and sometimes it'll actually also go up. because it starts fluctuating, right? So this is something that we have to experiment and control based on the data. It all depends on the data that we have. We can't basically say there's a perfect learning rate. So all depends on the data and the kind of network that we build, how complex the network that we build. So that is one question called learning rate. So we understood what a perceptron is, what's the input layer, what's the hidden layer, what's the output layer, what's an error function is, loss function. Okay. Whether these loss functions are different for different kind of problems. So typically we use for classification problems. I think we'll come back later, we'll look at it when we actually start the session. We use something called log loss function or cross entropy function, right? So these error functions are very important to define. And we have to specifically mention that when we actually build a neural network model. And then we also understood what is a feed forward and what is a back propagation model. What's the back propagation step? Okay. And also what's a gradient descent step? Okay. Any questions so far?
Yeah, I just have one question, but I think this is related to the very initial slide when you were comparing with that neural network has surpassed the human intelligence as well, that ImageNet. I mean, just out of curiosity, I'm asking. Slide number 10, I believe.
Yeah, please ask.
Right. It says that it has surpassed the human intelligence as well, right? I mean,
Oh,
the
yeah,
way the
yeah.
human is interacting. I mean, how do we judge that? I mean, to validate something, we again rely on the human intelligence, right?
Correct.
How does that basically validated as human intelligence has been not able to check that?
No, initial test set is created by the humans, of course. Okay, you cannot you cannot surpass that, right? The human validation set is created by the humans. Then what you do is you do some kind of augmentation, right? For example, you create some images. Let's say there are 100 images are there, right? So see, you have to do a proper comparison, right? So you take these 100 images, let's say, and then let's say you blur some of the images. You create another 100 images out of that, but out of the 10 images, you blur it, like a Turing test. Now, these images you show to the algorithm and show to another human being.
Understood.
Right? And then see who does better.
All right.
Right. So that's basically it's not, of course, you cannot surpass the test set validation who created it, but this is the typical Turing test that we do, right? And same thing also. For example, let's say if you had heard about this particular case study, I just, because that's an interesting question. This typically I saw this case study, detecting diabetic eye disease, right? So the only way to detect the diabetic condition in the eye is if you can go to an ophthalmologist, right? And then you take a retina scan and show it, the doctor will say, okay, this is suffering from this condition and not this condition, isn't it? So what they do is, when they run this model, their performance was, they actually built a deep learning model to automatically detect this condition. Their accuracy was 0.995 compared to the typical ophthalmologist score of 0.91. So they actually better detect it. But you might ask the same question, how can you even do that? Right? So even the ophthalmologist cannot determine how can you surpass their accuracy score. So here what they did is, they took each image and asked at least a panel of 3 to 7 ophthalmologists to can detect the condition. Because if you ask one ophthalmologist, probably there could be bias or there could be error or mistake, isn't it? But if you ask each one at least a panel of 3 to 7, isn't it? Then probably it'd be better diagnosed.
Right.
But of course, you can't compare performance with that, because as a patient, I will never go to 3 to 7 ophthalmologists. Can I go? Right? I'll probably go to 1 or 2 second opinion. So they have to simulate that scenario. That's why they took a median score. So they took, okay, let's look at how the model is performing. Vis-a-vis in the real world, the patient goes to 1 or 2 ophthalmologists at max, what the performance is, and then see how we are doing better with that. Of course, we can never beat this panel of 3 to 7 ophthalmologists.
Understood. So this
Yeah.
0.91 is basically for one ophthalmologist, right? In
1
general.
or 2 max.
1 or 2.
Yeah.
Understood.
Yeah.
Makes sense.
Yeah. When it's a human level performance, that means basically in the real world, how do we actually perform in the right use cases? Can we beat that? Okay. Yeah.
Got it. Answer my question. Thanks.
Okay. Thank you. And probably we'll take a 10-15 minutes break and come back and look at the example.
Right.
Yeah.
So it's right now. What's the time?
8:45.
Right. We'll be back
Just
with
come
9.
9. Exactly 9 will start.
Right. Okay. Thanks.
Okay, welcome everyone. I will going to post this link again. So if you can go to the GitHub link, I'm pasting it in chat window. So this is github.com, Manoranjan P, Gen AI _ LLM. All right. If you go there, I'll just wait for 30 seconds for everyone to go there. You can go to this folder called DL intro. And below, if you see, there's the introduction to deep learning, open in Colab. So right click on this and say open in new tab. This will open the notebook. So I'm sure most of you, or probably all of you, are familiar with the Google Colab. So here you can say connect. Will connect to the machine. Virtual, basically provision a virtual machine for you. Our LLM course will also be mostly driven by Google Colab, but of course there'll be some hands-on will be on the local systems also. And here I'm taking actually a Boston house price prediction example. And I build a small neural network model, and basically we'll go through all these concepts from the practical hands-on perspective. So I'll get started now. So this Boston house prediction is about predicting the price of houses in a particular town or locality. You can assume like that, right? So what's a median price of a house in a particular locality in terms of $100,000? Now, in terms of $1,000. Now, to understand the price of houses in a particular locality, there are some factors which can actually help us determine that. For example, what's a crime rate by the town? What's a proportionate of residential lands zone for lots over 25,000 square feet lands? What's a proportion of non-retail businesses across per town, whether it's beside Salz River or not? What's a pollution level, right? What's a index of accessibility to radial highways, right? So quite a few important parameters are there, which can actually help us determine what's the median price of the house, right? So this is, of course, a classic example of a regression problem, right? My Y value is also a continuous value. So I can actually calculate MSE to understand how good the model is. But rather than using a simple linear regression, we'll build a simple deep learning model. So now let's import the required libraries here, pandas, and read the CSV file. The CSV file is now pointing to the GitHub location only, this particular data file called boston.csv. And then if you look at some of the data sets, some of the samples. Okay, so this particular house, median price of the houses in this locality is about $24,000. And these are the different parameters. Okay, it is not besides the Charles River, and so many other different parameters, and so on and so forth, right? How many samples we have? We have about 333 samples, right? Not much here, but this is a good example to try to demonstrate the capability and how basically deep learning, you can actually build models and all that. But in the meantime, I just want to check. Can you just say yes on the chat window if you're able to open and run it, load the data, just to ensure that you all are able to do it. Can you simply say yes on the chat window, please? Please go ahead and say yes on the chat window if you're able to load the notebook and execute. Any specific problem, Abin?
It's giving me name error, trace back most. So I don't know when I'm running, it's giving me a name error. So maybe it's a company. I don't know what's the issue is.
Okay, there might be some restrictions should be there. Okay.
Okay.
So I'll go ahead. Probably you can try it later. Huh?
Sure.
Okay, I'm going to say set an X and Y variables. So all the variables except the median prices are going to be my X values. So X1, X2, X3. And my Y is going to be the median value. Okay. So if you look at the shape, so 13 variables. That means when I build a neural network, my number of parameters input layer neurons would be 13. And my output is of course 1, the median prices, right? So I'll go first to split the data into train and test. So train, test, split X and Y, and I'm going to split it by 80-20 ratio. And I'm going to name those train and test as the train X, train Y, test X, and test Y. So this contains the X values for the train, X values for the test, Y values for the train, and Y values for test, right? So my sample got split into 266 samples for train and 67 for test data. Okay. First, I'm going to go and normalize the data. This is one of the prerequisites for learning deep learning models. Your data has to be on the same scale, right? Same scale. Okay. This is for the gradient descent, the delta calculation. And there are multiple different techniques to normalize the data. One is called mean max scaler, and then one standard scaler. Right. In the mean max scaler, what you do is, for example, you want to scale the values of crime rate or age, because you can see these are all decimal values. These are in terms of tens, or probably 100, right? And this is probably hundreds. So they are definitely not on the same scale. You have to bring them to all the same scale. But normally what we do is for example, we take this value, subtract the minimum value in this particular column. So you take any xi minus x minimum, divide by the x max minus x minimum, right? What is the value here with respect to the minimum and the maximum crime rate? Okay, so this value of course will be always between 0 to 1. So if you do a min max scaling, it will always be 0 to 1. But most widely used technique is called standard scaling, because we normally assume these variables follow normal distribution. So rather than doing a min max scaling, you can take the value minus the average value of it. What's average crime rate? Divide by the standard deviation. Okay. So these values typically will remain between -3 to +3 because your normal distribution, they look at the bell curve, most of the population will lie between -3 standard deviation to the +3 standard deviation. Okay, so everything will fall into that. But whichever technique you use, right, it will bring all the values into one single scale. In this case, of course, I'm going to use standard scaling. So I'm going to calculate the mean and the standard deviation for all the X values, subtract the mean, divide by the standard deviation, and repeat the whole process for train and test data. Okay, so this will ensure that all the data are brought into one single scale. Okay, this is a prerequisite for running your optimizers. And then build the N1 model. Now you come to building the neural network model, the actual deep learning model. So I'm going to use, for example, for building neural network model, there are of course quite a few libraries are there. So here are some of the libraries that you can be leveraged, like a TensorFlow. PyTorch are the most promising two leading libraries. In fact, there are other libraries which also has some amount of implementations. Even scikit-learn also has a perceptron library. But they are typically low-level libraries. What they have done is they built an abstraction called Keras. By the way, today Keras supports both PyTorch and TensorFlow, and also supports a new library called JAX as well. So Keras is very simple library to kind of run all these build neural network models. But so we're going to leverage that now in this particular exercise. So let's import TensorFlow and Keras. And typically it's a good idea to always check the version number. So all libraries, by the way, in Python, you must be aware already. Any library, you should say dot, that library, dot, like if, for example, let's say your pandas, right? PD dot, dash, dash, sorry, underscore, underscore, 2 underscores, version underscore, underscore, right? This will give you the version number always. It's always going to give the version number. Now, we'll go and build a model. So here I'm going to build a very simple model which contains only 2 hidden layers. So in this case, what happens is I'm going to, the way you actually create a model is simply say add. Okay, sequential, you keep add layers after layers, and then simply keep adding different layers to it. Right? You just say model add dense 64. Dense 64 means you're adding a hidden layer here. So you have a input layer, right? You have an input layer. And then we are adding a new hidden layer, which contains 64 neurons, by the way. Okay. And when you add the first hidden layer, you have to specify how many inputs it will receive. Right? So you have to give it the input shape. Now, if you see here, I have specified the number of inputs, which is nothing but your train X, right? Shape 1. Now, if you go back and say the train X shape 1 is basically 13. It's saying that then 13 number of neurons are there, input neurons. So that you have to specify for the first hidden layer always, because it does not know how many inputs it will receive. So we are saying that there will be a hidden layer of 64 neurons, and is going to receive 13 input neurons, the data from the 13 input neurons. And I'm going to add an activation layer to that. How this particular hidden layer neurons would be activated. the activation function, because the summation function is fixed, that we cannot change anyway. So moment you say 64 neurons, the first function that every neuron will do is summation function that basically comes out of all these input neurons. Only you have to specify the activation function, right? So I'm going to use an activation function called ReLU. By the way, there are quite a few of them are there, but three most widely used activation functions are your sigmoid functions, TANH function, and a ReLU function. Sigmoid function, like I told you, whatever input that comes, it will always transform the data, and the output will always be between 0 and 1, right? It's always remain 0 to 1, irrespective of what the x value is. TANH function, whatever the input is, so this will be always between 0 to 1, the output, when you activate or transform it. TANH function will always be between -1 to +1. Okay. And the ReLU function is typically a pass-through function. Okay. But it also controls the negative values. So if the input is a negative value, it remains 0. And moment it comes positive values, it remains as it is. So the ReLU function is like this. The function ReLU function fx is, it is equal to 0 when when x is less than equal to 0, and it's equal to x when x is more than 0, right? This is how the function looks like. Okay. This is most widely used nowadays. Of course, it has its own variations also called leaky ReLU and all that, but this is most widely used primarily because of the gradient. Okay, so the constant learning. We'll have to learn some of the advanced concepts later, but these are the three primary functions that we use. So in this case, of course, we are going to use a ReLU function. And we're going to activate that. Then we are going to add one more layer of hidden layer, which again contains 64 neurons and again ReLU activation, right? So now we have an input layer with 13, one hidden layer with 64, another hidden layer with 64, and one, finally the output layer is one neuron. Okay, you see that the final, I'm going to use just one neuron because my output is simply a regression continuous value, like a median price. And I'm not going to add an activation because that's going to the final Y value here. Okay. Now, each of these layers, activation is defined as a ReLU and ReLU. So this is my model now. Okay. And I can also now look at the summary of the model. This will be interesting. Now, if you see, now this is basically saying that this total number of parameters is about 5,121 number of neurons. Now, it also shows how many parameters on each layer. For example, the first layer is my input neuron X1 to X30, and the next layer is neuron N1 to N64. Now, how many connections should be there? How many weights should be there between these two? So that will be 13 multiplied by 64, right? Weights will be there. And of course, each of these neurons will have a bias term, right? Remember, every neuron. So plus 64. So if you multiply this and plus 64, it will come to 896. You can actually do that. So if I look at 13 multiplied by 64, right, plus 64. So that comes to 896. So you're saying that between the first dense layer, okay, the concept of dense, when you say dense layer, is basically fully connected layer. That means this layer is fully connected with the previous layer and fully connected with the next layer. That's the whole idea of a dense layer. Now the next layer is what? This is between the input layer and the first hidden layer. The second hidden layer is connected to the previous hidden layer. So it must be 64 multiplied by 64 plus 64. Again, neurons are there. So now if I do that, let's say 64 multiplied by 64 plus 64, that comes out to 4160, right? So that number of weights connections has to be estimated. That means this means number of parameters has to be estimated. Then there's 65 because in the final hidden layer, 64 neurons are there and one output layer. So 64 connections, 64 multiplied by 1 plus 1 bias term here plus 1. So that's basically 65, right? So understand, very clear here. And we have totally how many? 5,121 number of parameters are there. Any questions on this one so far? Just to check. Yeah, please ask the question. Somebody asked.
Right. Himanshu here again.
Yeah, sure.
So in this case, we have taken two layers in between, right?
Yeah.
In between the outcome and the input, right? So selection of activation function. I'm just curious on to learn to that part. That do we just simply? I mean, can we select two different activation function for different layers?
Yes,
Right?
yes, absolutely.
And
Different layers, but within layer you cannot choose different functions.
within layer we cannot. But
Yeah.
what is the criteria to choose, or like let's say select ReLU, or to go with sigmoid, or to 10H? Any like you said, it's a trial and error, or we have a certain objective or the thought process to select any particular activation function?
So of course, there's some little advanced concepts are there. I'll come to that probably later.
Mhm.
There's something called vanishing gradient, right? For example, empirical they have found over a period of time, ReLU typically works better. So if you look at most of the modern models, deep learning models, most people are using ReLU models, ReLU activation functions by default. Okay. So earlier people were using sigmoid and tan. Probably most people are not using anymore. Okay. But you can still experiment and see which works best. My take is ReLU will still work better. The reason is what happens is when you calculate the gradient, the delta values, right? Okay. You see, if it reaches, the value reaches to the 1 point, let's say it saturates here, right? If you calculate the gradient here, typically the gradient becomes what? Almost? Zero. So there is no learning that happens. But here, if you see, the gradient is always what? Positive value, right? So that's why typically ReLU works better compared to other activation functions. And say ReLU was not detected earlier. Earlier, people were using in the initial times sigmoid or tan as most.
I remember.
Yeah. And of course, ReLU also has its different versions, like a leaky ReLU there. So some people told it simply cannot, set to 0 when the negative values are there. It has to some slope to calculate the learning. So now leaky ReLU has a little bit of slope on the negative side and positive side has a higher slope. So to answer your question,
just one more question.
You try one activation function and you see that loss is not reducing later much. Then if you're not use ReLU, try ReLU.
Okay.
Yeah.
All right. And selection of number of perceptron. Is it also like we can go with 64 or 48 or any number?
Yeah.
That
typically it's any number. That's again a big exercise. Okay. That's why what happens is nowadays people come with a standard architecture.
Okay.
People researchers, for example, if you look at a computer vision, people have VGG18, right? Inception. So these are people who would have experimented with a different number of layers and neurons and all that. Typically, it's not possible for us to kind of experiment with 100 possible combinations and all that, right? So that's why the people come with the standard architecture. So you can leverage that and probably can little bit of modifications. You can do that. Okay.
Okay. Thanks.
Any other Khushbu, you're asking some question?
Yeah, hi Manoranjan. Thank you for the session. I have a very quick question. So, on the beginning of this code, when you're fitting in the model, it says model.sequential. Is it because we are going from one dense to the another dense, which is basically one set of layer to another set of layer?
Correct.
So, okay. And
Yeah.
are there any other models which are
Yeah, also there.
non-sequential?
Yeah, also there. We'll come to that later.
Okay.
This is a
Okay.
simplistic
Okay.
form.
Thank you.
Yeah.
Okay.
And once you define the model, we can actually have to set all these values. Now, this is the important part, and we have already gone through that. For example, we have to specify what is the optimizer we're going to use. Remember, we discussed. So for this model, we are going to use a gradient descent. Little bit of variations of that called stochastic gradient descent. Again, same concept, little variations are there. Then what loss function? MSE, because it's a regression model, right? So three important parameters has to be, variables has to be set here. What optimizer you will use to learn. Okay, so this you can use, in this case, gradient descent. What is the loss function? How do I calculate loss? Right, that has to be set. And ultimately, how do I validate this model with the test data? Right, that also I'm going to use MSE, but you can also use R square, by the way, here, regression model. Okay, so now these values would change based on two things. One is what problem you are solving. Like, for example, if you're solving a classification problem, right, classify whether this positive or negative, or churn or not churn, fraud or not fraud, then your loss function will change. Optimizer probably can use the same thing. Your loss function will be your cross entropy function. In your metrics, typically classification models, we use something called precision recall or total accuracy or ROC AOC score. So these two has to be appropriately set based on the problem that you're solving. Okay, so that has to be very careful. But in this case, it's a regression model, so you're going to use a gradient descent, MSE, and MSE for all three of them. Okay, so let's execute that one. And then we will use something called epochs. Okay, so this is nothing but your number of iterations. Okay, number of iterations that we're going to use, feed forward and backward. Right, now that's a little bit of variation, different concept there. I'll explain that, and then we'll actually fit the model. The difference between an epoch and iteration is, now typical deep learning models will run using thousands of data sets, or probably 10,000s or millions of data points, right? Now imagine that we have a 10,000 data points. Okay, you have 10,000 sample sets. Now S1 to, let's say, S1 10,000. Now you build a neural network model, right? You have a neurons in different hidden layer, and then you are giving the input, let's say your sample S1, and then you calculate the Y value. Okay, so you will feed all the samples from S1 to what, S10,000, and then you'll get all the values, and then you'll calculate the loss function, loss value using the loss function, isn't it? So that's basically one feed forward. And then you do a back propagation, right? And you adjust the weights. Again, you feed all the 10,000 samples. You calculate the loss value, because loss value is nothing but your Y minus YA hat, I equal to 1 to n. That's the number of samples, 1 by n, right? Across all samples. Then if you see here, of course, 10,000 samples also is very small. But when you look at, if you look at your GPT models, right? They're actually trained on a 4 trillion tokens, right? So it's a very large data set. It's natural to use hundreds, millions, or billions of data points. Then every time if you feed the whole data, just to make one adjustment, right, is going to take a lot of computational resource. Okay, so then they came this idea is that you don't have to feed the whole data to learn. What instead you can do, instead you split this whole sample set into something called batches, right? Some small batches, right? So it's a batch one. Let's say I can say 100 samples each batch. So batch one, batch two, batch 3, right? 100 some. So there'll probably 10,000, still 1,000 batches should be, or sorry, 100 batches should be there. Okay, whatever it is. Now, of course, these batches should be created very randomly and created. Then what they're saying is, you simply send one batch only, batch 1. One simple batch you send it. Then immediately calculate the loss function. Okay, and then you make an adjustment to the weights. And the next time you send the second batch. Okay, and then your third batch, then fourth batch. You see that every time you're quickly learning. First of all, you're quickly learning with only 100 samples, some adjustments you're doing. And every time you're learning with the new data, of course, that's basically you're not overfitting also, right? So the learning process happens much faster. Instead of sending all 10,000 and computing, then doing adjustment, you can learn much, much faster. Okay. So what happens is when you send all these batches and come to the end of the whole batch, so last batch is sent. Okay. And you see that the loss is still reducing. So you have to still continue learning because you have not learned everything now. You still have to learn. So exhausting all the batches is called one epoch, by the way. Exhausting all the batches is called one epoch. Then you again start. Whatever the loss function is, loss is there at this point in time, again you start with the batch 1. Either you can use the same batches or reshuffle them and create new batches. That again you can take a call that is configurable. Okay. And then you run again one more epoch, right? So exhausting all the batches is called one epoch, right? But the batch size is how much data point you will send each time to learn. Okay. So that's the difference between the batch size and epochs. So here I'm saying that 30 times you'll do it. Batch size by default is defined in the framework as a 32. Okay. So every time you're going to send 32 and 32, and we have how many samples total? I forgot. 226 training samples, right? So 226 divided by 226 divided by 32. Okay. So data will be converted into 8 batches. Okay, probably it's 8 batches. 7.0 means 8 batches. Because the last batch will be the remaining number of samples. It cannot be 32, always exactly remaining number of batches. So let's say epoch 30. And then now I'll fit the model. Model.fit train X, train Y, 30 epochs. And I'm also giving the validation data. The end of the each epoch is also going to test it against the test data and see how much is the accuracy. And accuracy I have already told, use MSE only to measure the accuracy here. Now what I'll do is now I will go ahead and now run the model. So go ahead and fit it. Okay. So it's basically, you can see that there are 30 batches are there. 30 epochs are there, 1 to 30. And at the end of each epoch, all right, at the end of each epoch, it's calculating the loss. So you see that this is the first epoch, 1 by 10, 2 by 10. So end of each epoch is calculating the loss. It's calculating the training loss and the test loss, the validation loss, against the validation data also. And one thing you'll see very clearly here is the loss initially was 463, then it reduced to 428, 322, 156. You can see it's reducing continuously. That means you're continuously learning. And every epoch, you basically, the new weights are estimated, of course, every batch. And you can see slowly it's coming down. And then it probably fluctuating around this particular point here, about 15 or 10. The same thing happens to the validation loss, also comes to the 8 or 7. Sorry, it also comes to 8. Okay. Of course, we can run more number of iterations. I'll come to one point called how to stop these iterations, when to stop. Now you can go and look at how these losses are reduced. So I've actually done a matplotlib plot, and you can look at the MSE and the loss both. Now you see that these are number of epochs here and the MSE. The MSE initially reduced and then it would shoot up again. And then it actually reduced now. Finally, the same thing happened to the loss also. Okay. So this little bit of, if you see the fluctuations that's happening here, if you look at towards the end, right? It primarily because happening, remember we discussed a concept called what? Learning rate. Maybe little learning rate is a little higher. Maybe it will control that. It probably will stabilize it. So the next one, what I'll do is I will actually same model I'm going to build. 64 neurons in the hidden layer, ReLU, 64 neurons in the hidden layer, ReLU. And then here I am initializing SGD with a learning rate of 0.001. Okay, typically I think it's 0.1 or something. So I'm going to say, okay, let's take a very small learning rate. Okay, let it gradually go rather than rapidly descending and probably start fluctuating. Let it go very slowly but gradually and stabilize the right. So I'm going to use SGD now, and then I'm going to use that now. And then of course the loss function, everything is correct. And this time I'm going to use little more number of epochs, 100 epochs probably. And hopefully it will stabilize a little bit. Yeah, you can see the better now. It's going to almost 7.6. So it actually reduced further. And if you look at the plot also, yeah, this is a little much smoother descent, and it's almost fine, stabilizing on a minimum point. The MSE error. Okay. So probably if you reduce the learning rate, probably it needs more iterations, but slowly, gradually descends and kind of stabilizes on the lower loss value. Okay, we're getting a better model, more optimal value model. Everybody is able to run this model fit. A couple of more concepts I'm going to cover before I close down. Something called callback. Okay, let's also, once the model is built, let's say this is the model that we're going to use finally, this model. Then I can actually use that model to predict on the test data finally. This is by deploying. And then I can also measure the accuracy using the metrics, mean squared error. Okay, matrix is not defined. Let's define that. I think I forgot. So from sklearn, import matrix. Can you write this before this? From scikit-learn, import matrix. Yeah. So the mean squared error is actually RMSE. I'm taking a square root of it. So first I'm calculating the mean squared error, the MSE. Right, I'm taking a square root of it, which is of course known as root mean squared error, you probably know. And it comes out to be 2.6. So I can interpret this value very naively, of course. This is, of course, is a standard deviation estimation, but naively I can say that if I take this particular model that I have built here and going to predict the median value of the houses, right? The median value of the price of the houses. If basically predict saying that, okay, the median value is about $50,000, you can think like this is a plus or minus of 2.61, right? So this is how the price would be. That much error we have, but pretty good actually compared to that. $2,000 here and there, $2,600, right? That's a mean error. but this is actually a standard deviation estimate, but you can naively kind of interpret that value like that. Okay. Now, a couple of important points here. Then one question is how many epochs you want to run? 100, 200, 300, right? Or can we dynamically control this learning rate? Because if you look at a loss function, right? Let's say it looks like something like convex function. We don't need to slow down here if we are here. We might probably take a larger step, but when you actually approach the valley, the lower point, then we'll slow down. You don't have to slow down here. Then you can learn better, faster, right? But if you start taking small steps from the beginning only, we'll need more iterations. So rather than taking a constant learning rate of 0.01, can we dynamically control it, right? Saying that later you take, right? So there are two questions. One is how many epochs I need to run, okay? Because if you also look at our example here, we probably could have stopped somewhere, much earlier, like around 60, 50 and all that, because we already reached the point of 8 and we are not going anywhere, probably not much going down. So there is a callback method that we can apply. One is called early stopping, right? Can you actually build a mechanism to stop early if we think we are not learning any better? So rather than learning all, let's say I will use 1,000 iterations. Typically in the real world, we use 1,000, 2,000 iterations and all that. But then if you're not learning after, let's say 500 iterations, there's no point in unnecessarily, spending computational resource and run it. Second one is reduce the learning rate on plateau, on the valley, rather than reducing in the beginning. So you can control that by adding these callback methods. Reduce LR on plateau. So how much to reduce? You reduce by factor of 0.1. So if it's already 0.1, you reduce to 0.01. If it's already 0.01, you reduce to 0.001. So you basically do a factor, is always factor. And when to do it, you observe, this is a parameter called patience. You observe for 3 epochs. Let's say I'm running hundreds of epochs, right? After, let's say, 11th, 10th epoch, the loss value is, let's say, 8. But the 11th, 12th, and 13th, now the loss function is about 8.1, 8, and 8.2. That means it's either remains constant or it's increasing. That means you know that it's fluctuating. It's not going any down. Then you do what? You reduce the LR and try. So there you basically, then probably it will go down. It will say 10.8 and all that. Okay. So how many epochs you will observe, right? To decide whether it has to be further reduced, that you can factor in here. Now, second one is, even after you reduce the LR, let's say it's still not reducing, right? Then you can use early stopping, like a patience. So you observe for 6 times, and let's say in 6 times you're still not reducing, then basically you'll say, can you stop it there? We don't need to learn anymore. But of course, this has to be clearly, probably you'll use little more value, little bigger value. Just for demonstration, I have typically used lesser value, maybe 10 or 20 or something that you'll use. And then there's something called a model checkpoint, okay, which ensures that when the loss function is reduced and if, let's say, it again increases, okay, it always keeps track of the model which always gave the least loss, okay, and that it checkpoints to the file path. Somewhere it's going to store it. Okay, that you can leverage to deploy it. Okay, so from Keras callback, reduce LR on plateau, early stopping, and model checkpoint. You can do that. Then build the model. Of course, this is, you can reuse the previous one also, but just to completely show the
Himanshu here. Can you elaborate model checkpoint one more time, please?
Model checkpoint is, now let's say early stopping, right? Let's say at the iteration of 15, my loss was 8, 16, 17, 18, 19, 20, right? 1, 2, 3, 4, 5, 6. It was 8.2, 8.1, let's say 8, 8.2, and 8.3, right? So you know that this particular loss is not reducing, right? Either remains constant or basically increasing, isn't it? So there is no point in running more iteration now, more epochs. So I'll stop it here. So when I stop it here, whether I want to take the model that is at the end of this iteration, or I want to take the model at the iteration where it gives the best loss function, right? So what it does is it basically checkpoints, save the best only.
Okay.
And it basically takes this particular model, okay, which gives the least loss.
All right. That's great. Thank you.
And then if you run it, let's say 100 epochs now here. Let's see how many epochs. Yeah, you can see that at the 23 epochs, it stopped. 1, 2, 3. Even though I gave 100, at 23 epochs, it stopped. That primarily because if I am, let me look at it. Look at the validation loss. No? Look at the. So I'm basically, it also tells I have to specify what to look at to take the decision, the validation loss. Right? If you see here, I think this is the best we got validation loss. Right? 9.00 or 8.95. I think this is the, yeah, this is the minimum we got. Then 1, 2, 3, 4, 5, 6. You can see the next 6 steps. It actually gave a more loss than this one, right? That's why I decided to stop it here. 6 steps. Because, okay, I've already got the loss and the next 6 steps has not helped me. So let me stop here. And if you also look at the learning rates, if you see here at this point of time, the learning rate was initially 0.0050. Is that correct? I forgot. Yeah, 0.005. And if you also look at here, right, this was the validation loss 9.62. Then actually it increased 28, 10, and 15. 3 times because they're given patients 3 times. And then they decide, okay, it's not helping me. So let's reduce by a factor of 10.1. So it will reduce to 0.0005 now here. And that actually helped and it started reducing. See, that's the beauty of it. Because on the plateau, when it starts fluctuating or increasing, I reduced the learning rate and started reducing further now. Okay, until this point where it actually again had to reduce further here. So 8, then it remained constant, again give, but did not help anymore. And the whole iteration, the epochs has to be stopped. Okay. So this is, of course, you can use little higher value. Just for demonstration example, I've used very small values. You observe it for like 10, 20 epochs and then take these decisions in a real world. Okay. And ultimately, of course, you can save the model. Why is it taking so long? You can save the model and then you can simply say model.save. You're going to save it to the local system. And you can also load the model from the local system. Okay, H5 is basically a format to store the deep learning models, the weights, and then you can predict that as well. Okay, I'm not sure why it's not. Yeah, it's coming. So save the model.save, and if you look at the folder, this folder icon here, you see that the file is created here, Boston House model.h5. But I think by default, if you don't do save also, though I have explicitly done it here, I think the checkpoint would have actually saved that model there. Okay, you don't have to explicitly say save the model here. The checkpoint itself would have created this model. Yeah, it's not required. You will actually find a file like this, and then you can load the model now, let's say for deployment, and you predict, and you can compare, right? For example, I load the model and I take one particular house data and predict at what price the house would be sold. At what are medium price of houses in that particular locality. It says about $24,000. So that's basically an end-to-end demonstration of, right, how these deep learning models are created. A simple model though, but it also covers most of the concepts: feed-forward, optimizers, learning rate, right, loss function. All these concepts basically explains very nicely. Okay, so I probably suggest you to kind of go through this one more time if possible, and if possible, little play around with this. For example, change the number of neurons, add a number of more layers, change these functions to sigmoid function or tan functions, right, and see how it kind of affects the errors. You can take the last model where you define the early stopping criteria and reduce LR, and there you can actually kind of modify this. It will play around with this and see if you can reduce the loss below 8.5, right? That'd be very nice to kind of experiment. Okay. So that kind of brings us to the end of this session. I'm going to stop it here, and I'm going to, of course, stop the recordings also.